Well, I have two such reagents right now. We won't need the first one today. I'll make a separate video about it in the future. That was iron pentacarbonyl. Hey guys, what do you think about unpacking chemicals? As you know, people like to watch YouTubers unpack different gadgets and bunch of other stuff, so I thought that unpackings like the one that you see right now might be interesting to many of you who watch my videos. Now let me know what you think about this in the comments, and if you don't like the idea, I will not include any unpackings in the following videos, so it saves you some time. Like many other liquid chemical reagents from Sigma, iron pentacarbonyl is also packed in absorbent cloth, in case the can with the reagent gets damaged during the transpiration. By the way, a reagent package often costs more than the reagent itself. So now we'll cut the package, take out our reagent and move on to the chemical reactions. Those chemical reagents that are highly sensitive to the air have a self-sealing silicon gasket, and they should be collected with a syringe. Iron pentacarbonyl is not as dangerous as Tert-butyl lithium, so I just fill the syringe with it without passing argon through the can. Iron pentacarbonyl is a yellow-red oily liquid, and I would say it smells like stinky rubber. A transient contact with humid air results in the formation of a reddish precipitation in liquid iron pentacarbonyl that consists of the decay products of this reagent. It's mostly iron-free oxides and hydroxides and also other carbonyl complexes. If iron pentacarbonyl is cooled down to the temperature of liquid nitrogen, it will turn pale yellow. Increasing the temperature of iron pentacarbonyl makes it become darker, and at the temperature above 150 degrees Celsius it starts to decompose into metallic iron, iron-free oxide and carbon monoxide. You can spot carbon monoxide by the darkening of an iodine pentoxide crystal. A forming metallic mirror on the tube walls is significantly tainted by other products of iron pentacarbonyl decay, mainly by its iron-free oxide. You can say that judging by its brown color. To get extra pure iron, the decomposition of iron pentacarbonyl is performed by carefully heating it in the inert gas atmosphere. I'll perform this reaction in the tube that I connected to the argon flow. Along with iron pentacarbonyl vapors, you can notice the formation of a black tint on the tube walls. This is a metallic mirror that consists of extra pure iron. The yellow vapors of iron pentacarbonyl are not visible anymore, which means we can take the iron that we got out of the tube completely safely. To make sure it's iron, we can put a magnet to it. The rest of the metallic mirror on the tube walls may be dissolved in hydrochloric acid. Iron pentacarbonyl is inflammable, but it burns with a naked flame not that often. In most cases, when it contacts with fire, you will observe its decomposition with no flame whatsoever. In the end, we got the mixture of iron oxides 2 and 3. If iron pentacarbonyl is born in pure oxygen, we'll get a practically pure iron-free oxide. It's quite interesting that burning iron pentacarbonyl didn't react with nitrous oxide in any way, considering that usually any burning matter burns even more intensely on contact with it. The solution of iron pentacarbonyl in ether reacts with sulfuric acid, forming ferrous sulfate, hydrogen and carbon monoxide. The solution of iron trichloride in acetone oxidizes iron in carbonyl to ferrous iron. The solution of copper dichloride in acetone acts the same way. This reaction results in the formation of white crystals, which are copper monochloride. It is insoluble in acetone. Dichromic acid reacts with iron pentacarbonyl, forming iron oxide hydrate, chromia and carbon dioxide. Many articles covering iron pentacarbonyl mention its tendency to photolysis, that is, to decompose on exposure to light. A mercury vapor lamp or a wood lamp or a UVA light decomposes iron pentacarbonyl very quickly. My laser, with a 450 nanometers wavelength, can do it too. This experiment will be much more effective if we dissolve iron pentacarbonyl in methanol. Also, iron pentacarbonyl alcohol solution has reducing properties, as it's capable of reducing silver from silver nitrate solution. The Wikipedia article about iron pentacarbonyl says that irradiation of pentacarbonyl with UV produces nanocarbonyl. It's indeed so, although you need not just any iron pentacarbonyl, but its solution in acetic acid or pyridine, so the reaction would have a high yield. Unlike methanol, iron pentacarbonyl is very soluble in pyridine, forming a bright orange solution. Now take a look at how the iron nanocarbonyl forms and gravitates to the bottom of the tube under the effect of the laser. Let's see how the iron nanocarbonyl crystals look at a very close range. Some time ago I posted a reaction from this video in the community tab, asking you to guess both reagents that react so violently with each other. Horse Steaks was the first who guessed iron pentacarbonyl, but nobody guessed the other reagent. It was Tert-butyl hydroperoxide. Tert-butyl hydroperoxide is an extremely dangerous compound. According to some sources, it has an enthalpy rating of 444. Well, it is true for pure tert-butyl hydroperoxide, however, they always use its solution in a laboratory practice. But even a 70% solution can self-ignite on contact with some oxidizers, such as chromium trioxide and manganese heptoxide, for example. Organic peroxides oxidize iron pentacarbonyl to brown iron-free oxide so effectively that this reaction is used to prove the presence of peroxides in hydrocarbons. And this is what happens when tert-butyl hydroperoxide and iron pentacarbonyl react with each other. Thanks for watching, guys, I hope you really liked this video. Also huge thanks to my patrons. Their support makes it much easier for me to get all the chemicals I need for new videos. See you soon!